It's my pleasure tonight to introduce Doug Paul. Doug's been a member of the BCA Photo Group for what, less than a year probably?
Yeah.
And I've already recruited him. He's done a lot of work on this. And when I started talking to him about astrophotography, it's amazing how many areas that I didn't even know existed. So I'm really looking forward to this tonight. I'd like to give a little bio on Doug. Doug Paul's been an amateur photographer for most of his life, starting with a Kodak Brownie, progressing through a film SLR, then black and white darkroom and color slides to DSLRs. He learned landscape photography by exposure to his mother's photographs and started dabbling in fixed tripod astrophotography about 7 years ago. Since then, he's progressed to a tracking mount 3 years ago, followed by more serious deep space object imaging. There'll be a test on this later in case you're wondering. Doug is a retired electrical engineer. He's used some of his professional skills to understand the processing of astronomical images and to write programs for image acquisition and processing. So I'm looking forward to it. So all that software stuff is things that to me I didn't even know existed. So I'm really looking forward to hearing about it. Yep.
Okay, well, thank you. Okay, this is, actually I've only been doing this seriously for about 2 years. I'm only really an intermediate myself, so, we'll see how we can do. I started doing some fixed tripod stuff. You know, there's a bright thing up in the sky, so I tried aiming my camera at it and taking a picture. Those worked out. And I was reading some threads on Canon rumors about some people who were posting some knock your socks off images, and some even talked about how, and after a while I decided I can do that, so I dove in. So here we are. So the first part is basically pictorial progression from beginner to where I am now, and then once hopefully the hook is set and or it's well set, I'll go through how we actually do this. So the moon is a very easy target. It's a sunlit object. It's dark colored, so you need about 1 stop more exposure than a terrestrial sunlit scene. So you're going to do these things handheld. Well, that doesn't want to work. Oh, okay. There we go. More of the moon, the whole thing. And this next one is the same shot, but with the color saturation turned up, showing that there is color on the moon, and this is hints as to the composition of various rocks and the like. And this was looked out the back window, ran and grabbed the camera. A big snowstorm was coming in, and so this was a F8B there. I did have a chance after a while to go in and get a wider lens. And lunar eclipses are also pretty easy. They start nice and bright and get fairly dim. The exposures at full eclipse are well, it's dim enough that you start having problems with the moon moving on you. So this is the one in January this year. This is the early part of it. The blue up there is from ozone, and here's during totality. And you can shoot the planets. What's of interest in this one is this thing. That's Mercury. That's a transit of Mercury across the face of the sun. And by the way, there's another one coming up on November 11th. They last a few hours. You need a sun filter though. And then the next one, they happen about 13 times a century, so they don't happen that often. And this is Mercury directly. Mercury is always low in the sky, so the colors at the top and the bottom are from dispersive diffraction in the atmosphere. This is Venus with even stronger diffraction. This is Mars, and the white up on the top there is an ice cap. Some bands on Jupiter. Another shot of bands. The moons. Jupiter has 4 very bright moons. To get them, though, you have to overexpose the planet body. Conjunction in astronomy is when 2 objects of interest get close together. In this case, this is a triple. The Moon, Venus, and Mercury. This other little spot here that's a lens reflection. Oh, you probably can't see it on this, but there are a couple stars up in there. So this is, of course, just after sunset. Okay, you can do things with wide field lenses. For instance, this is a 10 millimeter lens, fixed tripod shot. Here's the Big Dipper, Pointer stars up here, and here's the Little Dipper. You should shoot a wide range of exposures on these because different things show at different exposure levels, and you can't really tell when you're looking at the back of your camera. And the sun, you need a sun filter for this or you will destroy your camera. If you look through your camera without the sun filter, you will destroy your eyes. So get a purpose-built sun filter for that. It's like an 18-stop ND filter with infrared and UV blocking. Just 18 stops in the visual band is not good enough. Then the 2017 solar eclipse. This is a beginning sliver, diamond ring. The blue there that's a lens flare. This is Bailey's beads. This is the edge of the sun showing through low spots on the limb of the moon. This is some more beads with some red prominences showing here. The next 3 shots were all taken within 3 seconds of each other. My camera can shoot a 7-shot bracket, which was very useful for this. I shot about 400 shots in the interesting 5 minutes. So this is a short exposure. This is a medium exposure. This is a longer exposure. Note the change of scale. This is half the scale of the other one. And the corona can go out to as much as about 6 sun radii, and this is about 6 sun radii here. Here's a star, I think that was Regulus. And this is the same picture as the previous one, but processed to show the moon. So that's the moon by Earthshine. And that's through a zoom lens too. It would have been even better if I had a prime. Okay, so this is prominences. The moon is moving left to right relative to the sun here, and so there are some prominences on the right side that are visible. And here's a close-up of those prominences. Then the exiting diamond ring, Zsa Zsa Gabor's diamond ring, and the final sliver. We had to leave about here, but I had 2 cameras running. What you've seen so far could have been taken on a fixed tripod. The next one is a time-lapse, which of course required a motorized drive. Oh, sorry, that's next. This is a high dynamic range shot. This is a combination of 7 shots at different exposures, processed to show more detail in the corona. And here's the time-lapse. So the Cookie Monster at work here. The drive wasn't aligned perfectly well, so occasionally it jumped. I could fix that in post, but haven't gotten around to it. And now a few shots of gear. This is an early version of the Eclipse shooting gear. This is a simple motor drive here, and this is the main camera, 100-400 millimeter lens, and then this is the time-lapse camera taking a shot every half second. this is a setting circle. Back on the drive here, well, it's not shown in this picture, but it's mounted right here on the drive. And on here, the declination bracket is I'll show you the declination scale. But these are the coordinates of the sky. I'll talk about that later. But right ascension and declination are like latitude and longitude, except they're attached to the sky. And so this is, I modified this drive to have both those scales. Here's the other one. And that turned it from a real nice toy into a serious instrument. This is the now higher performance rig. This is a 400 millimeter f2.8 lens. The camera's hidden behind it. There's a rain cover on it, and there's also a heater under there. This is an auto-guiding camera. It's a secondary camera which tracks a star and then feeds back error corrections to keep the guiding extra accurate. You can do up to 10, maybe 20-minute exposures with auto-guiding. The camera and lens here weigh about 10 pounds. The entire rest of this weighs about 90 pounds. So it's 90 pounds of support gear for the little 10 pounds of active gear or live gear. The tripod alone weighs 16 pounds. The head 34, that's 22 pounds of balance weight. This is much sturdier than your typical photographic tripod, and also takes a little longer to set up. This is the back view. Here's the auto guider with the camera on the back of a short telescope. Camera body's under here, and there are also 9 cables, or 9 wires, which drop down from here to an electronics box, which sits on the ground underneath. And okay, now the rest of it is shots taken with the motorized gear. So planets, you can get Saturn, and many of these are old. With my newer lenses and the like, I could probably do better. This is Saturn with 5 moons, which I've labeled here. This one's a star, but the rest of these here are all moons. And this is Uranus. And the classic way of identifying a planet is that you photograph it on several different nights and see if it moves. Well, it moves. And then here's Neptune, and similarly, it passes the move test. Here's Pluto, and it's the little one right there. And again, it moves as well. This is Ceres, an asteroid, and this is 2 shots about a half-hour apart, showing moving. And Vesta 1, another asteroid. Oops. Here we go. And now onto some wide field shots. These are done with things like, well, for instance, here, this is done with a 50 millimeter lens, f1 1.4. That's 10 shots of 30 seconds each, which were then combined to get the whole thing. But this is Andromeda, and if you know how to find Andromeda, you start with this star. See, Cassiopeia is out of sight to the left, but it points to this star for you, and then 1, 2, 3. This one bends low to the left, and Andromeda's right there. And then there's a line of bright stars, 1, 2, and the others are off the screen that help you. So if you know your sky, then this should jump out at you. By the way, this star is also a lot redder than it shows here.
Why do you need 10 shots?
Well, I was using the simple motor drive for this, and it cannot aim accurately for longer than about 30 seconds. In fact, at 30 seconds, with a 400 millimeter lens, I have to discard approximately half of the shots because of tracking error. The 50 millimeter lens is much easier for tracking, but the camera, at that point my software could only run the camera in manual mode, so 30 seconds was my maximum individual exposure. I'll go into detail about collecting them. The individual shots are called lights or subs for sub-exposures. But again, that'll cover heavily in the second part. Most of these pictures have the name of the object, the lens, and then 10, or the count times the number of subs in that. This is from a dark site up in Maine. Single shots of 30 seconds with my widest angle lens. So this is the northern part of the Milky Way. By the way, that's a satellite. I talk later on about how to eliminate those from your images. This is the center section. And the southern section. Yes, that's the Sagittarius region. This was a little Astro get-together, and those are the red lights of the other people down there. Okay, now the Messier objects. There are Charles Messier at the late 1700s made a catalog of objects, and they're a very popular list. They're relatively bright and easy to see. He used a 4-inch telescope from Paris back before there were electric lights and back before we had much pollution. Nowadays, they're a lot harder to see. So this one's 60. Most of these are shot with a 400mm f2.8 lens. So 60 subs times 30 seconds each. This is a globular cluster, M3. Another globular cluster, M4 crab, 53 subs. The M8, the Lagoon Nebula, 51 subs. M10, another globular cluster. M13, Great Star Cluster in Hercules. That's a very popular one. M17, the Omega Nebula. M20, the Trifid Nebula. This is a very nice one. A lot of people like it for its colors and counting in that group. And the noise here is, that's part of not collecting enough photons plus the effects of light pollution. M27, Dumbbell Nebula. M31, the Andromeda Galaxy, and then, let's see, M32 and M110. And that, I think those are, do I have those switched or is that correct? I think I have them correctly. Then M33, Triangle Galaxy.
Why was the M31? Why was the outside edge that pinkish color?
It's actually bluish, and that was one of the things that you do is you estimate and subtract off the background. And the background has, it's a three-dimensional background. It has colors to it, and how the exact levels and the color of the background is very important in. Has a very strong effect on the color of dim objects. If you look at better pictures of M31, there are lots of them out on the net. There is a very nice blue or delicate blue surround, and I had to tread the middle between eliminating background and saving the blue in this. I've tried to take better shots of it so far, but I haven't had a chance to completely process them. But look around the web, you will find some much nicer pictures, or ones which show the blue better. Does that answer your question? Sure. Yep. That's part of the art of bringing them out. There's a lot of artistic license in the processing. This is M33. Triangle Galaxy, M42, the Orion Nebula, and Demarian's Nebula, and then this is the Running Man Nebula up here. Right in here is called the Trapezium. That's 4 very bright stars. And the first time I took this with my standard exposures, it was this bright section was way overexposed, and I had to reduce the exposure by 3 stops. And hoping that I could still get enough exposure to get the fainter outer sections, and I obviously succeeded here. This is downsampled on full resolution copy. You can see the 4 stars individually. This star, by the way, is the middle star of Orion's sword. It's visible to the naked eye as a star. With binoculars, you can see a little bit of the nebulosity. This is the Pleiades, also a naked eye object, but you won't see the nebulosity by eye. I don't think you'll see it with binocs either. This is M51, 2 interacting galaxies. This little galaxy is believed to have gone through the big one and is now just gone away and is now on its way back in, and you can see it's pulled out an arm of the main galaxy. M55 Spectre cluster, that's another globular cluster. This is M57 Ring Nebula. This is a so-called planetary nebula, which are shells of gas expelled by old red giants. By the way, this was shot at 1200 millimeters. That's my maximum focal length. M61 Swelling Spiral. M63 Sunflower Galaxy. The Leo triplets. These 2 are in the Messier list. This one isn't, but I think this is the interesting one. Hamburger Galaxy, for obvious reasons, and the dark stripe there is that's due to dust. M74 Phantom Galaxy. M76 Little Dumbbell Nebula. M78 Casper Friendly Ghost Nebula. Obviously, the people who named these have imaginations. This is M81 and M82, popular viewing targets. M83 Southern Pinwheel Galaxy. And this is M84 and 86. These 2 are on the Messier list, but there are over 15 galaxies in this image. 1, 2, 3, 4, 5, 6, 7, 8, with a cloud in between. 9, 10, 11, 12, 13, 14, 15. I probably missed 1 or 2. M88, M90, M91, M92, M94 Croxide, another planetary nebula, Owl Nebula, M97, M98, M99, M100, Blow Dryer, M101 Pinwheel, M102 Spindle, M104 Sombrero Galaxy, M106, M107, M108, M109 Vacuum Cleaner. That's obviously a modern name. All of those pictures, almost all of those pictures, in fact, in the M series here, all of these were taken from my backyard here in Bedford, horrible light pollution and all. I'm amazed that I'm able to do that well, given how horrible the light pollution is. Okay, a couple nebulae. This is the Flame Nebula, the Horsehead Nebula. This is the back star of Orion's belt. It shines in ultraviolet, which causes the gas here to fluoresce here as well. And then there's dark dust clouds in front of it to cause the shapes, flame and then Horsehead, which some of you have seen before. This is the North American Nebula. However, the first time it came up on the screen, it came up like this, so I think it should be called the Pink Elephant Nebula. This is Witchhead Nebula. Here's the chin, the nose, the big eye socket, the forehead. This is a really dim object. So yeah, that's what, about 35 minutes of data. sorry, about 38 minutes of data, and I have another that I have up to about 2.5 hours of data in it, but it has some problems with it. But I've seen pictures of that with enough data in it, and they're spectacular. This is the Veil Nebula. This was taken from the dark side in Maine again. This is also pretty dim. These parts are pretty bright, but this section is very dim. Was there a question? Okay. And this is, I repeated it with almost exactly the same shooting parameters from my backyard in Bedford. And you can see the dim stuff is gone. And back again. This is about 2 hours of accumulated data. And some comets. This was a Giacome's inner. This was done with a fixed tripod. This was done on a motorized tripod. This was the one in December. 12 days before totality, 8 days, 4 days, and then totality was clouded in. And there was a luminous blue. There was an announcement of luminous blue variable in M51. A luminous blue variable is a blue star. Its intensity changes significantly. And I looked at my image of it, this one, and found I'd taken it about 2 weeks before the announcement. So I then reshot it, and right there, the tick marks, you can see the blue variable. And there was the recent image of the surrounding light field from the black hole in M87. This was my standard shot of M87, and I looked. Well, maybe you could imagine a slight thing sticking out on the upper right. And here it is at 3 times magnification. And yeah, maybe, but it's a little iffy. So that was shot at 400 millimeters, and the limiting resolution was my sensor. So I upped it to 1200 millimeters, and there's the jet. The guy who reported it had used a 32-inch scope and HDR processing to show it. Okay, that's the eye candy. This is now the how. Question?
Yeah, on the previous shot, I don't know if you can go back to that. You've got
sorry, can't.
That's okay. 64 times 30. Does that mean that there's 32 hours worth of data in that image?
No, that would be 32 times 30 seconds, most likely.
Right, you had 64 times 30. So
okay, so that would be about 30 minutes.
30 minutes or 30 hours?
No, minutes.
30 minutes, okay.
Yeah. The units on the right are all either seconds or there's the Veil Nebula stuff is 2 minutes or so. Gradually working up to longer and longer subs on some of the dimmer objects. But around 5 minutes, if I shoot with my standard parameters from Bedford, the light pollution saturates my sensor. So, you know. Oh, sorry, I have to move the pointer. There we go. Okay. So, since this is a group of mostly non-astronomers, I'll give a little bit of basic astronomy. Then how to do the fixed mount, the easy stuff that any of us who have a tripod, a lens or two can do. Then, since I'll need them later, a very short course in statistics. That's a pretty easy course. You don't have to worry about it. Then how to do multiple exposures with a tracking mount. Then the image processing, and then finish up. So, okay, so basic astronomy. First of all, you need dark skies. Civil twilight is when the sun is 6 degrees below the horizon. Nautical twilight 12 and astronomical twilight 18. Well, it's worth waiting to astronomical twilight in the if you're in a dark site, but here with all the light pollution, it doesn't make nautical twilight to nautical twilight is fine. It doesn't really get any darker. Sometimes it feels like you could almost read a book, it's so bright out there. Sky glow, there are various forms, but you're not going to see them in Bedford. The moon is a major source of light pollution, but fortunately it's not there all the time. There's a Bortle scale for light pollution. It goes from 1 to 9, and Bedford's about 10. Sorry, about 8. Going downtown brings you to 9. Maybe 10. Okay, so quality of viewing, the atmosphere is a little like looking through, looking at something at the bottom of a pool of water. That it has ripples in it and moves around. Well, if you use the long telephoto trying to take a long distance shot, particularly on a hot day, you know the effect. Well, it happens aiming up too. And that causes stars to twinkle. And that typically limits your resolution to 1 or 2, about 1.5 to 2 arc seconds. 2 arc seconds is 1 inch of a mile and a half away. Transparency is also variable. Sometimes more light gets through than other times. Terminology. The meridian is the north-south line that goes directly overhead. Objects east of it are rising, west of it are sinking. And the best viewing occurs when the object is near the meridian, and the time when it crosses the meridian is called the transit. Locating objects, well, they're star charts, they're digital planaria, such as Stellaria happens to be the one I use. And there's a coordinate system, right ascension, which does east-west, and that's in hours, or actually hours, minutes, seconds, 0 to 24 hours. And then the 4 minutes of right ascension is equal to 1 degree. And declination is north-south, minus 90 degrees to plus 90 degrees, just like a flat line. For right ascension, once a reference point crosses the meridian, then it's the time till the object of interest crosses the meridian. So finding them. Well, if you have setting circles on the drive, you can use the coordinates. Star hopping is another way. You start from a known star, and then you hop a progression of stars over to your target of interest. Very hard to do with a camera, by the way. It's much easier to do with something that you're viewing through an eyepiece. You can do angle estimation by hand. A finger is 2 degrees wide. Your hand is 10 degrees. Your spread hand is 20 degrees. You can estimate angles from the field of view of your viewing device. For instance, my binoculars are about 5-degree field of view. So as you step across the sky, you can use that to measure how far you're going. A red dot finder is a device that projects, if you look through it, it projects a red dot out in infinity. It's used in many gun sights. Many of you may be familiar with it there. And that can be a big help. You can aim a camera to within a ½ degree or less. Sighting down a telephoto lens does not work very well, I assure you. And many telescopes also have a finder scope, a small about 5 times scope with crosshairs to help aim. Finding with a camera, you can, if you have a zoom lens, you can use the trick of focusing at full focal length, because you'll need that later. Then you zoom out and hope that the focus stays good enough. Take a picture, and you now have a wide enough field of view that you can tell where you are. Center it, and then zoom back in, and you have a good chance of being on your target. There's a brightness scale of magnitudes. That one magnitude is the 5th root of 100. It's about 2.5 or 1.33 stops.
And 31 is that problem?
Is it? Oh, sorry.
Typo.
Some, or think of, whichever. Strange spell checker didn't find that at all. I have to get a better one. For instance, the moon is -4. The dimmest object that I can see from Bedford is about 4.5. M31 is 5.7. And the dimmest that you can see with from the dark side is about 7.5 to 8. So I have seen Andromeda from the dark side. And the dimmest I can photograph is about -8, or is about 18, and the dimmest visible to professionals is about 30. And so that's for stars which are basically points. You cannot resolve the area. But for objects that you can resolve the area, like galaxies and the like, well, Andromeda is 14, and my dimmest image is about 18. Dark adaptation for your eye takes about 30 minutes for full adaptation, and use only dim red lights because white light will destroy your adaptation. There's also a trick called averted vision. Instead of looking directly at your target, look, say, 5 degrees away. I tend to look up, choose your direction, whatever works best for you. And your eye is more sensitive, slightly off the center of vision. So there are too many color cones in the center of your eye, which crowd out the rods, which are the dim receptors. So you have to move to the side to get more rods. And one can see a lot with just binoculars. You don't need fancy gear. In fact, you can see a lot with just your naked eye. However, get away from Bedford if you want to see much. If you want to see more, let's put it that way. Imaging equipment. In the Astro game, it's called an optical tube assembly. Telescope, well, a telescope designed for photography is called an astrograph. And you may need a field flattener because the focus is actually a curved surface, so you may need to flatten that so the entire image is in focus, and also you'll need an external focuser and so forth. And those can be refracted or mirrored. Camera lenses have a built-in flat field, they have built-in focus, and autofocus lenses include a focus motor. You generally use them wide open unless you have to stop down to reduce aberrations. And optical quality is very important. That the shape of a star image is determined by the characteristics of the lens. So it will show any imperfections in your lens. Sensors, DSLRs make good sensors, but modern ones are surprisingly good. Astro-specific ones, you can have in color. It's called one-shot color in Astro game, or monochrome. And if you want to shoot color with monochrome, use external filters and combine them. After that, you may also cool the camera to reduce leakage. I'll talk about leakage later, but that's effectively another form of light pollution. And everything, by the time morning rolls around, everything will be soaking wet or covered in frost. You might as well just take a hose and spray your gear from the start. Dew gets on everything. So a lens hood helps. In the Astro game, that's called a dew shield. And lens heaters, electrical are best. There's also a kind of hand warmer called Easy Heat, which it's a super saturated solution. You trigger it, and then it gives off heat for the next hour. Most hand warmers or other kinds give off exhaust gases that can damage your gear. So if you use hand warmers, use the Easy Heat ones, and you can recharge them, so you can use them forever. I attach mine to the lens with an ace bandage. And I use DSLRs for sensors. The 80D and 6D are two of the better ones. Oh, the 90D specs, the 90D, which is just out, the specs on it, looking pretty good. And my lenses range from 10 millimeter to 1200 millimeter focal length. Now the fixed mount single exposure imaging. Camera lenses can be used as a form of a refracting telescope. Larger apertures gather more light and have more resolution, but the larger aperture is more likely to be degraded by seeing conditions. And lenses are practical for up to about 6 inches. By the way, in the Astro game, when you give a single number, it's the diameter of your lens or your mirror, it's not your focal length. How much light you gather is the single most important thing. So up to about 6 inches is about the biggest lenses go these days. The largest one that's been in real use is 40 inches. So 6-inch apertures have a resolution of about 0.8 arc seconds. So that's what 8/10 of an inch at 3 miles. And again, seeing typically limits your resolution to about 2 arc seconds. 6-inch apertures are pretty common for 400 to 600 millimeter lenses, or focal length lens or mirror. And 400 millimeters focal length is a 3 by 2 degree field of view for APS-C sensor, 5 by 3.5 for full frame. And wide angles are good for constellations and the like. The 10 millimeter one has a 96 by 73 degree field of view, bigger for full frame. And even modest lenses can work pretty well. I used a 100-400 f5.6 lens for, quite successfully. And you use manual focus and turn off image stabilization and autofocus. Your automation basically doesn't work when it comes to Astro. Okay, fixed mount basics. Use short exposures, seconds or fractions of seconds for sharp images, or long exposures, hours, if you want to get the streaked, circular streaked images, which many people like to do. Use whatever ISO you want for single shots. The same applies as for terrestrial shots. However, if you're stacking them, combining them, that's different. Also, somebody in a previous meeting, a woman asked about having some noise bands on her camera when she pushed the image. Try increasing your ISO is one way to reduce those, and I'll talk about more powerful methods soon. The focus, you use magnified live view, aim at a bright star, and focus it. An articulating screen is very handy here, so you don't have to try to sit under it and look up at it. It's a godsend. You need a very sturdy tripod, a ball head. You can use a ball head for a wide angle, but a geared head is very, very helpful for a telephoto. You can get away with a pan head, but the others are probably better when it comes down to it. And you need to be able to shoot straight up, and many heads will not do that, but they will shoot straight down. So mount your camera backwards. Vibration control, these things are absolutely the most sensitive things around for vibration. If you walk near the tripod when the shutter's open, you can streak your photograph. I have a rule of thumb of never get within 10 feet of the camera when it's running. And to shoot, use remote shutter actuation with mirror lockup and a delayed shutter to let the mirror vibration die out. Or you could use live view, but live view beats the sensor. That increases your noise, so that's okay. You can get away with it for single shots of bright objects, but when it gets down to the dim stuff, nope.
Some cameras have both mechanical and electronic shutter you can choose what you're going to use. Is it ever bad to use the electronic shutter? It has no vibration, but
your target, if you're tracking it properly, your target isn't moving much. You don't have to worry about moving shutter.
I'm talking about vibration from the...
Oh, vibration. Well, electronic shutter will cause any vibration.
Is there a disadvantage? I don't know.
Not that I know of.
Okay.
I have mechanical shutters, so I've never actually done electronic shutter, but I believe it should work. Let's see, okay. Oops, just a little slow. Okay. The airy disk, a star, with the exception of our sun, with amateur gear, a star is a point of light. You cannot resolve any area, so that the image shape is determined by diffraction and the f-stop, and of course your lens aberrations. So for a perfect lens, this is what the image looks like. That's for color. so that you get the colored bands farther out. But basically, it's the a constant times the wavelength times the f-stop gives you the diameter. They are measured null to null, and since the wavelengths vary for different colors, that's why you get color bands. For a dim star, you see the just the center peak. But if it's brighter, as the star gets brighter, that peak will grow bigger and bigger. It gets really bright. Then you'll see skirts or halos out there from the sides of the distribution. At that point, the center is likely to be saturated. So your stars are too small to resolve. So your image size is determined by the aperture, the lens. The aperture, the diffraction on your aperture, the lens aberrations, your sensor resolution. For instance, my 400 millimeter f2.8 lens out-resolves my sensor, and seeing conditions. The Earth is, of course, rotating, so well, 360 degrees in 24 hours comes down to 15 degrees an hour, or a quarter of a degree per minute, 4 minutes per degree if you prefer, or 15 arc seconds per second. My images are resolving down to, say, 2 arc seconds. So at 15 seconds, that's what, in a quarter of a second or so, you smear the image. And the worst is near zero declination, the celestial equator. Whereas if you're shooting Polaris, for instance, right near the pole, I can shoot 30 seconds on a fixed tripod and not have smearing. So the rule of thumb is that you experiment around where you divide some number n by your focal length. And that number is typically 50 to about 500 or 600, depending on the f-stop, your sensor resolution, your lens quality, desired sharpness. If you're shooting for a postage stamp size image, well, you can shoot a lot longer than if you're shooting for a full-size sharp image. And near the poles, you can divide n by the cosine of the declination to see how much longer you can go. You can also estimate n from geometry if you like to play with math, but ultimately you have to do it by trial, verify it by trial and error. So, okay, some targets that are suitable for a fixed mount. The moon, dark colored, think asphalt pavement, and sunlit, so about 1 stop greater than the sun's heat. So you can handhold a telephoto shooting lens if you want. The moon is about half a degree in diameter, so the maximum focal length is 2,400 millimeters for full frame, or 1,600 for APS-C. APS-C is crop factor about 1.6, not used to the destination. The sun is the same diameter. Use a sun filter if you value A, your camera, and B, your eyes. It's a good way to go blind if you don't use the filters, and get a purpose-built filter. That way you can guarantee that it has not only the necessary blocking in the visual range, but also in the ultraviolet and infrared area. They tend to be either aluminum film or a polymer film. And you aim by the camera shadow and then use live view. So if you're smart, you don't even look through the thing, look through your camera at all. The planets are, well, the inner planets, Mercury, Venus, Mars, Jupiter, are all shootable from a fixed tripod. Serious planetary imaging uses very long focal lengths, greater than 2,000 millimeters. I've seen a Mars picture taken by somebody at 9,000 millimeters. And what's called lucky imaging, you basically take a movie and then you after the fact, if you look at it, it's rippling and moving around. But after the fact, you choose the few good frames and average them, and people can get some amazing things like that. They're momentary. They're moments of clarity. And by shooting essentially a movie, you get them. Or if you can't shoot a movie, well, my movie is low resolution, but my regular shots are high resolution. So I just put the camera in auto repeat mode or machine gun mode, hold the button down, take a few hundred shots, and go back and look at them later. I have a bunch of that stuff that I haven't had a chance to process yet, but I might have some better pictures of some of the planets that I showed you earlier. So for exposure now, again, manual controls, your auto exposure doesn't work. You might be able to autofocus on the moon, but beyond that, don't try it. It won't work. So you have to do all that manual. The sun and the moon, you might be able to use the histogram. But planet bodies are so small that they're not visible on the average camera histogram. Although if you have saturation blinkers, it may be too small for you to see them. Maybe they'll work, maybe they won't. Examine the image on the screen with maximum magnification and bracket. You'd be surprised how different it looks on your computer indoors, afterwards. Or just shoot a spread. I started out by just shooting wide spreads, and I'd find a range of maybe 2 stops when we come out. And shoot several shots at every exposure, because again, the atmosphere is wavering in and out. And try some manual lucky imaging. And I've written a program which starts at 1/8,000th of a second and just keeps on taking 1 stop longer exposures until something saturates and then stops, so that I can quickly, when a planet's the brightest thing in my field of view, I know that's going to saturate first, so I just aim the camera at it and fire up this program, and it tells me the exposure quickly. But that's a special purpose thing. Planetary moons, well, you saw some in my shots. You generally have to overexpose the planet body to get them. For constellations or other wide field of view things, try a range of exposures. But at different exposures, different things show up. And you can't tell until you look at it on the big screen. And even with the best exposures, you can expect the brighter stars to saturate. And shoot RAW, or RAW plus JPEG. RAW has greater dynamic range, and if you're going to do advanced processing, you definitely want RAW. So, okay, now we'll move on to what you can do with the tracking mount and multiple exposures. So this is the pay dirt, shall we say. Let's see. Better mounts have. Oh, sure. Sorry. You have an equatorial mount, which means that it's aligned to the Earth's rotation. So one axis is parallel to the Earth's axis of rotation, and that's right ascension. And then the declination axis does north-south. It gets a little while to get used to aiming in that domain. And the right ascension axis is motorized to cancel the Earth's rotation. And the better mounts also have a motor on the declination axis. The German equatorial mount is the most common kind of equatorial mount used by amateur photographers. This allows longer exposures, say up to 10-ish minutes with auto guiding. And you can do, depending on the quality of the drive, you can do 30 seconds without guiding. And this makes multiple exposure practical that can be combined into any length exposure. And if you do it right, you can combine exposures from multiple nights and so forth. And many better mounts are computer controlled. You have go-to, you can simply type in an object name and it will go to it, or type in coordinates. And those can be integrated with the computer to control both the mount and the camera. There are also altitude azimuth mounts that are fine for eyepiece viewing, but not as good for imaging. And the image field also rotates so that it'll tend to smear your image anyhow. So you have to have a derotator, and it's better to avoid it from the start. Okay, camera control. You need remote actuation with mirror lockup and delayed shutter release to let the vibration delay. I have a choice of 3-second or 10-second. I needed 10 seconds for my simpler mount. 3 seconds is good enough for the better now. But I've also gone to computer control. Intervalometers are devices that will enable you to shoot time lapse, shoot a large number of shots just by a timer. And they can also be used as a shutter release. So you put an extension cord on them so that you waste about 5 to 8 feet just into the ground, tie it to the leg of your tripod, and then get 10 feet or more away and operate it from a distance. And you can also have it, set it up to do 10 to 20 shots and walk away from it. So you do it for focus, you do have to refocus periodically. The temperature changes as your aim changes, gravity may affect it differently, and so forth. So, if you don't have a bright star in your field of view, you'll have to slew away, find a bright star, refocus, slew back, and that can be troublesome. You can end up losing the object, and so forth. So, with a good go-to mount, you can have it automatically come back, but with a manually controlled mount, it can be easy to hit the target. My software-controlled autofocus has the advantage that I can aim anywhere at the sky, and there are enough stars there that it can focus. And so I just do a manual focus before starting, and then take an 8-second exposure, download it, compute a focus figure of merit, step the focus and repeat, and then choose the focus with the best setting or best figure of merit. And go with it. It takes about 2 minutes, so every 10 or 20 shots, just refocus, and it's great. There are times that I've had, well, the temperature's been steady, and then it changes, and you can see the temperature change in the focus setting. And attempt to mark each kind of exposure with a different focal length. Then, if you have to say resort them off your memory card, something like that, then you can tell which is which. I use 20 seconds for aiming shots, 8 seconds for focus, and my lights or subs are 30 or more seconds. But with computer control, I can download each. As I download each one, I can store it in a separate directory so that everything's pretty organized. Yes?
Maybe I missed this, but are you saying that you need to refocus due to changes in atmospheric conditions?
Well, temperature mostly. I don't think you need to refocus because the atmosphere changes, just the degree of turbulence changes, and so your seeing may go up or down. But
so your own personal seeing might go up or down?
No, seeing is the generic name used for how well your eye or a telescope can see through the sky. It's, turbulence is the antithesis of seeing. So again, it's sort of like looking through at an object in a pool of water with some waves on it. So the focus doesn't really change with seeing.
I'm just trying to reconcile if you've got no matter what the focal length of the lens is, it's that far away. You're focused on infinity.
But because of thermal expansion and contraction in the physical structure, etc., then it will go out of focus. And you
just have to keep adjusting it.
And you have to keep refocusing. Most photographers don't focus and then keep shooting at that exact same focus for an hour or more. You may refocus every shot, and it only has to stay in focus for a few minutes at most. This game's different. Let's see. Okay. So for computerized control of the mount, aim the mount by either, I can name it from my planetarium program, and take an aiming shot, and if need be, then move the camera a little bit to get the object that I want centered. Then I start the auto guider to stay on target. And then I fire up the camera control program, which raises the mirror, waits a few seconds, and then sets the exposure parameters and starts to shoot and download images, as many as I want, and then periodically I have it stop and refocus, again all automatically. So for a typical session, say the exposure is 30 seconds, ISO 800, shoot 40 images and refocus every 10. And that will take about a half hour. And then when it's done, release the mirror. Meanwhile, I can go off and I'll sit back and monitor, plan the next object, go inside, have a snack, go to the bathroom. If it's cold, warm up, whatever. And one of the things that as I'm shooting the images, as each one comes in, within a few seconds of the shutter closing, it's downloaded on the computer and displayed so that I can keep an eye on what it's doing. That's a big help. And now a very short course in statistics. Don't worry, the math is all simple here. The complicated part will be ignored. It's just there for completeness in case there's anybody with statistical OCD in the audience. So you have a set of n data points. You have x's, you have n of them, and we all know how to take an average. You just add them up and divide by n. Then there's the standard deviation, which is you take that average from each data point, you subtract the average, square, add it up, divide by n, and take the square root. That's a measure of how broadly they are spread out. And depending on the details, if you compute the average from the data set, then you use n-1 here. If the average came independently, you use n. So if I'm flipping a coin, and say I flip it 100 times, and I get, what, 40 heads, then, well, the average would be 40 as far as I know, so I use 40 in this equation. But if I told you it's a fair coin ahead of time, and that the average should be 50, then that 50 came independently, and you use this equation. So it's a case of whether the average is derived from the same data or not. That's a relatively fine point that probably most of you needn't worry about too much. And as n gets big, the two are very close. And then the variance is basically just the square of the standard deviation. But again, they're both measures of how widely the data is spread. The median is the center value of a sorted list of points. You just sort them by their value, take the middle one. And that's sometimes used instead of an average, but it's most useful only for small n. In some cases, that data spread it would be noise. That let's say it's a pixel of an image. Well, you want the exact value of the average amount of light coming from that pixel. Well, you can't have it. All you can have is your estimates. And so the spread in those data points gives you, or those estimates, gives you a notion of the amount of noise in the data. Okay, this is one probability distribution. This is the Poisson distribution. It's for things like photon counts and electron counts. So we can't count photons directly, but we can count electrons knocked loose by them. So in any case, it's count of discrete objects. And you can't, of course, a negative value doesn't make any sense, but it can be 0 or anything positive. So you have an average count of lambda, and then you have the standard deviation for that is the square root of lambda, or square root of the average count. The only thing we need to worry about further on here is the average and the standard deviation. Similarly, the Gaussian probability distribution, also known as normal distribution, or popularly known as the bell curve. This applies to electronics noise, on an FM radio when you tune it off a station, or an amplifier when you turn it way up and just hear the background. That's that kind of noise. Here's the equation. We can ignore that, but here are graphs of several Gaussians with as the standard deviation sigma gets larger, then they spread, and the spread gets wider. And one more quantization error. This is the uniform probability distribution. when you're quantizing the signal, your analog to digital converter, you basically put your analog voltage in, and then it effectively snaps to the closest digital level. So, then, now if it were out here, it would snap to the next guy. So that your probability distribution here is uniform across that level. And this is half the step size, minus half the step size to the entire step size. And actually, we won't have to worry about the standard deviation of it. But, so now signal averaging. And averaging is just addition followed by division by n. So addition and averaging are the same thing as far as this discussion is concerned. When you have statistically dependent things or correlated things, the same things, for instance, you're taking a picture and you add some noise to it, and you add random noise, and you take 10 of these images with different random noise each time. The picture part is the same each time. That's correlated. And when you add them up, that adds arithmetically. So when you add them up, you have 10 times the picture. Now the noise, however, technically statistically independent noise, adds in variance, not in actual value. So that you square the values, you add them up, and then you take the square root. So the noise, if you add up 10 objects, the picture part will go up by 10. The noise will go up by about 3.1 or 3.2, square root of 10. So this is vitally important in being able to extract pictures out of the noise and light pollution. And the signal-to-noise ratio, the ratio of the standard deviations of the signal and the noise, improves as the square root of n. So astro imaging. Now this is the signal architecture of your camera. The photons come in, go through light filters, and then slam into the sensor. And about 50% of those photons knock an electron loose in the sensor, which is collected in quantum wells is the technical name. You can think of them as buckets that store the electrons, and the capacity of each of these wells is about 2,000 electrons per square micron. So if you know you look up in your camera specs, you see how big your pixels are, and you can estimate how many electrons can be fit in there. There's also leakage into the well. That's tunneling, carrying electrons into the well, but basically electrons leak into the well. This adds read noise, or adds noise to the signal. These are Poisson distributed. And also the photoelectrons are also Poisson. So this all, and then when you read it out, you get some read noise with the Gaussian distribution. And then the signal, okay, so effectively you add read noise here. Then you have an amplifier, and this amplifier sets the ISO. So for instance, if that gain is 1 for an ISO of 100, it's 2 for 200, and so forth. But in the process, if that gain is now 2, well, if a gain of 1, a full sensor well goes to the full range, full setting on the ADD. Now when you set a gain to 2, the top half of the, filling the top half of the well will just saturate the ADD. So you lose that gain as you turn your ISO up. So the amplifier also contributes to the read noise, and these are all generally specified as equivalent sensor read noises. So all the noise that's picked up here is mapped back to here, and then you assume that the gain, the amplifier is perfect. Some cameras also have the ADD off chip to pick up electrical noise on the wires, causing a reduced dynamic range. And in fact, if you've seen dynamic range versus ISO curves of some cameras, for some it looks like this. For others, it continues up like this. This is, well, Canon had this problem on their earlier cameras, but their most recent cameras are like this. The difference is that they moved the ADD onto the sensor chip. And when it's off the chip, then you you pick up noise in the wires here going from one chip to another, and that caused the roll-off in dynamic range. Whereas by moving the A to D on chip, you don't pick up that noise, and you get much higher ISO, much higher dynamic range at low ISO. So Nikon and Sony did that earlier on. Okay, then you add an offset. At this point, while your signal is always non-negative, your signal plus noise can go negative. So you have to add an offset before it goes to the A to D. So now you represent negative values here. Let's see, Nikon, some of the later Nikon 800 series do this. Canon has always done this, at least in the Canons that I'm aware of. I don't know about other manufacturers. But like some of the Canon 800s, Nikon 800 series make good Astro cameras, but the earlier ones don't. The problem is if you take an average, when you've clipped all the negative values away, then you're not getting the right average, you're getting the wrong value. The A to D converter adds some noise, but we'll deal with that. And then your output, that's your output that goes to your raw file. Actually, one other thing that you want, at this point, some manufacturers insist on fooling with the data to make it better. Sony, for instance, and that destroys the camera as an Astro sensor. So, sorry, Sony owners. Sony has a reputation for eating stars. Well, that's where they put their star eating. Then the noise sources. Okay, light has noise. It's inherently built in because it arrives as discrete photons. And that noise is the square root of the number of photons. Well, in this case, we can't sense the photons directly, but we do sense the photoelectrons, the electrons that are knocked loose by the photons. But they have the same Poisson statistics. So the square root of the number of photoelectrons is the photoelectron noise. Then you have leakage, some additional electrons that sneak in, and you have a rate, lambda sub L here times the time, which gives you the total number of, expected total number of leakage electrons, and your noise, your standard deviation is the square root of that. But you can reduce the leakage by cooling the sensor. It about halves the leakage every about 5 degrees C that you lower it. You also have pixel zero variation. That if you put no light in the camera and assume everything's noiseless, each pixel will give you a slightly different value. So you have to measure that and cancel that out. And that's done by dark subtraction, which I'll describe later. Then there's pixel non-uniform sensitivity. That let's say you put a bright uniform, you have a very bright uniform scene. Then because the pixels have slightly different sensitivities, that will then look like noise in the picture. And of course, there's also vignetting, which makes the center more sensitive than the edges and so forth. So we reduce both of those by flats. Again, more detail later. And the read noise, which is Gaussian, depends on the ISO. That's the sensor plus amplifier noise. And there's A to D noise, which is uniform, which depends on also on the ISO. But and if that step size is too big, in other words, too low an ISO, then the noise will become correlated with the signal, and essentially become part of the signal. And your averaging will now amplify it instead of reducing it. So you choosing the right ISO is important. And then so at low levels, the noise is dominated by the read noise and the pixel zero variation. At medium levels, electron noise, and high levels by pixel non-uniformity. So you start with the raw images, and I've already spoken to, we need real raw, not doctored raw. The basic processing is to calibrate the image is you take your lights, those are your shots of your targets. Lights or subs, subtract the darks, and divide by the flats. Now, subtracting the darks removes that pixel zero variation. Then the flats again, the pictures of a uniform field, then because they're less at the edges, say at the edges due to vignetting, when you divide by the number less than 1, it boosts it back up and cancels out your vignetting. This will also cancel. Subtracting the darks will also remove bands in your image. That's the more powerful method than just raising your ISO. Yes, we do take pictures, astrophotographers do take pictures of the insides of your lens cap, or body cap if you prefer. Those are darks and flats. Well, there's one common method, is the t-shirt method, that you put a couple layers of t-shirt over the front of your lens hood and aim it at a fairly uniform light source, either on an obstructed sky, or you can put a white window up on your computer screen, so it's all white, and aim at that. Make sure you're aiming straight onto it, and move around a little bit to average out variations. But take a bunch of pictures like that for flats. So now we have the calibrated image, so you register them. That is, you shift and rotate images so the features line up. And you stack, that is, combine the corresponding pixels. You estimate the background and subtract it off. And then for color, then you have to convert from sensor RGB color space to the sRGB color space. The sRGB is the color space that most computers run in and the internet runs in, etc. And then you stretch it, which is a nonlinear intensity mapping, to bring out the faint stuff and tone down the super bright stuff. Then you convert it to sRGB gamma, that's just to meet the standards, and then crop and perhaps edit to taste. And I do very light editing, maybe a little bit sharpening, typically nothing more. And if you end up downsampling it, that sharpens it anyhow, so you don't, and that reduces noise as well.
So are these flats storable? And you can have a whole series of flats?
Well, you have,
compare.
the flats have to be matched to the lens, the ISO, and actually I have, actually, why don't you hold your question for a moment, because I explain each of those in more detail. So, that's all right. So the darks are taken, again, with a lens cap on. They have to be time, ISO, and sensor temperature matched to the lights. Sensor temperature is in the EXIF data. And it measures the 0 point of each pixel, and the standard deviation measures your read noise. The biases, and that's the standard deviation there is for each pixel. If you have 100 flats, then you have 100 estimators for that pixel. So that's across the 100. That's not across the image itself. So there's sort of two ways of averaging. One is across your subs, and the other is across the imaging. And this is across your subs, or in this case, your darks.
Is the sensor temperature always in the IX? Is that a standard? Or is that
well, it's on all of my cameras. But check. EXIF tool is one of the best tools around for getting that. And
never noticed that.
Well, a number of other utilities may not print it out, is my point. The EXIF tool will print that and just about everything else out for you. I highly recommend it for anybody who doesn't have it. Biases, okay, bias frames are like darks, except they're shot with the shortest possible exposure time. So there's no time frame leakage. So sorry, those are the ones that will estimate the read noise for you. The standard deviation is the read noise, and the average is 0 point each pixel. So what happens in the longer darks or in the subs is that you have the 0 point variation plus leakage. And so by measuring both of them, you end up determining both of those. And flats are uniform source. Again, you have to have your lens, and your ISO matched. Also, your focus has to be at infinity for it. You take a bunch and then you average them again, and it measures the differences in pixel-to-pixel sensitivity. And also, if you have things like destendering, dust in your lens, it'll measure all that and you can take them out. However, if you clean your lens, then you've lost your, then you need new flats to correct for the new set of dust. And you make master darks and master flats according to their what they're sensitive to. So that after a while, you build up a library and you don't have to retake them all the time. So does that answer your question?
Yes, it does.
Okay. Okay, this is a master bias. If you look carefully, you can see a little bit of noise on it. It's also been pushed 9 stops. And it has a standard deviation of 4.2. This is a master dark. This is at 28 degrees C or 82 F. So there's a lot of leakage noise in this, which you can see readily here, as well as the standard deviation is 23. Yeah, 23. And this is the histograms. This is the
23 is the number of electrons?
that's all measured in electrons.
Thank you.
This is a master bias and this is a master dark, and you can see how there's a lot more push to the right on it. And I also looked at the master dark for 0C, and it looks almost like the bias. This is a flat. This is the full frame flat, and it's been pushed by about 3.5 stops. So it's highly exaggerated, but so that's what you see there mostly is vignetting. And this is the center detail at 100%, also pushed by a factor of 12 or 3.5 stops. And if you look carefully, you can see a small amount of pixel-to-pixel noise in that. So it's capturing both of them. So basically using these as part of how we push the camera well beyond where the designers actually designed for it. So for stacking, combining the sub-images, averaging is good, except it doesn't reject outliers, things like airplanes and satellites. Single clipped averaging is a procedure which I'll describe in detail later, which discards outliers and then averages the rest. And median, taking just the middle one, is very good at throwing out outliers, but it doesn't average, and that kills you with dim stuff. The dynamic range of Astro scenes can be as much as 30 stops, 22 magnitudes for the Astro crowd. Averaging increases the dynamic range of your image, and you can also combine it with HDR techniques. You take short exposures for bright stuff and longer exposures for dim stuff to help capture that dynamic range. Unfortunately, my software doesn't support HDR at this point, so I haven't done that. Then background estimation, you may need to level the background. The background may vary across your image, so you need to level that out. And then most of Astro images are dominated by the background. So if you take a histogram, the peaks of the histogram are your background, are first estimates for the background. And I usually add a small offset determined by trial and error to get the colors, or to get the final image. And then stretching, you can call it curves on steroids if you want. I'm using the pth root of the intensity, that can be written as with the root sign or exponent 1 over x, if either of those is familiar. For this notation, if p is 2, it's square root, if 3, it's cube root. But mathematically, that's well defined for numbers, for basically any number. And then you can adjust, so you adjust p by trial and error to bring out the features that you want. Here are some of those curves. So this is p equals 1, the steps of a half up to p equals 2.5. So you can see how this brings up the dim stuff while tamping down the bright stuff. And if you were doing this with a curves tool, if you move this point over to the right, that's the equivalent of dark subtraction. So you can do the whole thing with the curves tool. I just much prefer to do it this way. And I think this actually enables you to draw things here accurately that you have great difficulty drawing accurately with the curves tool. Okay, now sigma clipped averaging. It's a general statistical technique. Basically, you take a collection of data, say n data points, take the average of it or the median, and then you compute the standard deviation and multiply standard deviation by some small constant. 2 to 3 is typical, and that's so they reject any value that is greater than that threshold distance from the mean. So that throws away your outliers and leaves the rest for
Wasn't that going to throw away stars?
no. You do this per pixel.
Oh.
So if you have 100 subs with 24 million pixel image, you do this 24 million times on 100 data points at each.
Thank you.
So yes, no, it does not throw out stars. And typical outliers are things like airplanes, satellites, and meteors. I pointed out a satellite in an early image. Here is my best outlier, a low-flying airplane, and that's full frame. I discarded that manually, but I could have left that in the stack and it would have all disappeared. Okay, more image processing of color. So image, how you handle colors. The Bayer array has the RGB cell repeated throughout. So, and of course at each pixel, you have to estimate the missing 2 colors from the surround. And subtracting the RGB background affects the intensity of the colors as well as their saturation. So the first thing you do is you subtract the background, and then you apply the white balance. The white balance is multipliers on each color, and use a daylight white balance for natural colors in Astro. Then you convert from.
What do you mean by that?
So, for natural Astro colors.
Yes.
If you're if you're looking through a telescope, most images are dim enough that you can't see color. But if it's big enough and bright enough so that you can see color, that's the color you will perceive. So that the camera, of course, doesn't fail back to black and white. It stays colored all the way down. So you can get colors on very dim objects, and this makes them realistic. And one of the references that I'll cite at the end compares these photometric values of the color, and you basically get good colors this way. Now, if you're aiming close to the horizon, everything may be reddish, but for the same reason, the sun goes red when it gets low. But given your optical path, it gives you a natural color. Some Astro packages, well, I'm convinced that many Astro people don't know how to handle color well. Some packages will do things like set the averages of all 3 colors the same. So if your scene has a dominant color, it'll just map that all toward gray, desaturate them. If your package has that feature, don't use it. And in fact, I do my own. That's the white balance is applied in my own software in the processing. I don't let the package do that at all. I'll talk about specific software later. So then you convert from, after you've applied your white balance, you convert from sensor RGB to sRGB, and then you do the stretching, the nonlinear mapping, and if you apply that to the individual colors, you will desaturate. Instead, you make up an intensity by summing them, turn each color into the normalized one, that is, each one divided by the sum. You stretch the intensity or sum, and then you, those should be multiplies, not pluses there. Then you multiply the intensity by each of the normalized colors, and you get your colors back, but you have not damaged your saturation or your hue at all in this process. And that makes a major difference. And then eventually, at the tail end, you can convert to the sRGB, gamma and output. The normal processing in the camera, instead of subtracting what's up here, instead of subtracting the RGB background, you subtract that offset, and then you simply skip the stretch, and that's the processing for the normal camera. And if I turn those off in my stretching software, I get an output that looks virtually indistinguishable from the out-of-camera JPEG. Okay, so this is a 30-second sub, as it would process as if it came out of the camera. Here's a stretched version. This is what I see on my computer as I'm shooting. This is the stacked version with 113 of those subs stacked and presented as if it were out of camera. This is a stretch of the previous one. And then you crop it and scale it, and that's your final image. And for the histograms, this is the histogram of a sub. So those are your noise estimates, and you can see everything's low down here. This is 0 to 16,000, all 14 bits. And the vertical scale here is logs, so each tick mark is a factor of 10, and this is a 0. Since it's hard to plot log of 0, that's how I mapped it. So you can see that a lot of stuff has been pushed to the right here, and you can see a lot of saturation. Those are stars that I simply don't care about. Let saturate. Oh yes, one other thing, in checking exposure, this histogram, because I can do a log vertical, you can see the very small number of pixels on a planet or something like that. So I can use this to judge exposure, but the histogram on the back of the camera does not do that log for you. The advantage of writing your own tools. Okay, now total noise, temperature, exposure times, and so forth. The final question here is that if you want to expose for some fixed time, say an hour, how do you choose the number of subs? And of course, the number of subs times the time of each sub has to be an hour. So how do you choose what the right sub length is? So your total noise, and I squared both sides of the equation just to make it look similar. So this is all in variances. So the total variance is equal to the variance of each sub times n, then the leakage of each sub times n, and each read times n. You apply that constraint of the total time of, say, an hour, do a little bit of algebra, and you come up with, well, the total number of electrons is not a function of how many subs you have, so that drops out. Then the total number of leakage electrons is also not a function of how many subs you do, so that drops out, except, of course, we know that you can cool the sensor to reduce that. So the only remaining term of interest is the read noise, and you get one read noise for every sub. So, so you want to make the subs long enough that the two terms on the left are significantly larger than n times the read noise. But you also still want enough subs so that, well, the sub can't be so long that you can't track. Longer subs are more likely to have outliers in them. So you need to have enough subs, say 10 or more, so that you can eliminate outliers. You're also limited that you don't want the sensor to saturate. So staying within the bounds, you then choose something convenient. And typical times, I think most amateurs don't go beyond about 10 minutes. And one rule of thumb is that you can adjust the length of the subs so that the background peak on the histogram occurs about a third of the way across. That's another rule of thumb for choosing. And ISO, the following applies to stacked images. It does not apply to individual images. There's an interaction between the A to D converter and the averaging. Or the stacking process, which you have to take into account. So higher gain gives you higher ISO, gives you smaller A to D step size, all measured in electrons, and of course, reduced dynamic range. So here is a simulation where an image with a 1/10, 2/10, and so forth, 1 up to 2.5 electrons, image electrons are in each stub. We applied 3 electrons of read noise, took 100 simulated subs, and then adjusted the gain on them so that the step size is 2 electrodes per quantization step size down to 2/10. And you can see for these low ones, oh yes, the bottom one here is with no A to D and no added noise. And the next line is no A to D converter. So this is the best you can hope to achieve. So by the time you're down to about 0.3 electrons per step size, you're getting almost as good as the system without the A to D. So you choose the lowest A to D for which your step size is 0.3 electrons. And there are other concepts being thrown around like unity gain, which is this one up here, which 1 electron per step, which doesn't work well. And then ISO invariance, the thing that I briefly described over here on the whiteboard. And that you do things like choose this point. Well, that point, that's irrelevant. It might give you a good number, but it might not. Okay, so now this is how you actually calculate the ISO for your camera. Pixel full quantum well capacity is about 2,000 electrons per square micron of a pixel, and you assume that the full well capacity is max reading out of the A to D at base ISO. So the base ISO on my camera is 100. It's 14 bits, so that's about the max DN is about 16,000. And these numbers here also subtract off the offsets. So those are essentially the full well capacities minus the offsets. So here are the full 28,000 electrons, and then I have it for each step. And lo and behold, you get the magic, achieve the magic number at ISO 800. Your typical numbers are 800 to 3,200. And if you don't know what you're doing, try 1,600. I also calculated the read noise, which is 2.8 electrons, the leakage noise, and 7.5 stops in dynamic range. And I also use a 6D primarily because of the bigger sensor, that's a full frame, and 1,600. About the same analysis, 1,600.
From that chart, how do you actually decide that 800 is the best?
I'm sorry, how do you
decide that 800 is best?
Look at this number, electrons per step.
Yes.
And you go down it until you get below about 0.3.
Okay, why do you get 0.3?
That was the point of this.
Thank you. Okay.
Okay. So ran down that to 0.3 and chose the ISO. And now a little bit about the hardware. This is just what I use. There are plenty of alternatives. For tracking mounts, that first small one I showed you is the Skywatcher Star Adventure. It's modestly priced, it's basic, it's completely manual. I added the setting circles. It's also very good for learning your craft because you do everything manually. And then when I got a significantly more expensive, much higher performance, this is about 90 pounds of other stuff, Orion Atlas Pro drive. This also includes things like GoTo and computer control. I could use it exactly as I used the early one. In fact, that's how I did it. Initially, I just, it had setting circles, I just used them manually. And then as I learned to use the other features, I went over to them. But by learning my craft on the little one, I knew exactly what was going on with the biggie. And then if the lens is mounted by a foot, you can rotate it in the foot so that you can always rotate it to the best orientation, which is north up. And I'll talk about that in a moment. Then in camera bodies, I have the two. Some bodies are better than others. Lenses I have from 10 to 600 millimeters. and 1.4 and 2.0 extenders, so I go to 1200 millimeters. You can actually stack them and get 1680 millimeters, but I haven't quite verified that that gives me accurate image quality yet. And the larger the aperture, better. Primes are better than zooms, but you know, you can use anything. And again, astrophotography will show any imperfections in your lens. Software, there are many packages available, but I run Linux, and there weren't quite as many available for that. And most of what I describe here is available for PCs and Macs. So, and the codes OS are open source and CS closed source. So for the planetarium, I use Stellarium. That's open source. I put the, okay, that is, oh yeah, okay. That's open source, and it can also control your drive. And there's a cell phone version which costs a couple bucks, but it's very handy. As a mode, you can hold it up in the sky, and it'll give you a map of what you're looking at. Very good for beginners figuring out what they're looking at, i.e. moon. As an astronomer, I'm still very much a beginner. It can do, for camera controlled image download, I use G-Photo 2. Auto guiding PhD 2. The mount interface is Indy. Imaging session control, I wrote my own, but it uses G-Photo 2 to access the camera. Backyard EOS is a popular commercial package for PC. I wrote my own autofocus. I described it, and some of the commercial imaging session controllers can also autofocus. RAW, I use DC RAW for my RAW file conversion. Live RAW is also available, and there are many packages which do it as well. Image calibration and stacking, I use Regim. It's free, closed source. It's basic. It's good for beginner to intermediate, but I found a few problems in it, which you probably won't see initially. But it's easy to use. It'll teach you the basics, and it basically goes up as far as stacking, which is essentially a super raw, which you then have to stretch. So again, good for beginner to intermediate. It has good documentation. Stretching, I wrote my own. I decided it'd be harder to figure out. There are a lot of packages available, but I figured but it takes a while to learn enough about each one to decide whether you want it or not. So I decided it was easier just to write my own from scratch, and that's what I did. Yes?
When you write your own, are you using like Python, C, MATLAB?
Okay, my, let's see, my...
Probably not MATLAB, maybe you would pay for that.
No, there's a freeware version, or open source version. Let's see, autofocus is written in Perl. My imaging session controller is in C Shell. My stretcher is in C, but it spawns off sub-processors with pipes connected to do a number of things for me. So I borrow a number of other programs to use for.
Okay, so nothing's in like one package. This is all each step you're using.
Yep. I suspect that in most cases, well, you might be able to buy a commercial do-all, but in most cases, you have at least a few pieces. Well, things like PhD 2 is kind of the premier auto guide, and it runs standalone from everything. Well, it uses Indy. Indy is an interface program, but it runs independently of the camera control and so forth. And I've managed to get them all work together happily. Okay, let's see. And one of the things that my stretching can stretch from raw, as you've seen, as well as from a stacked image. It can basically stretch any normal image format. So, so I can use it both for viewing out in the field while I'm shooting, as well as for my final stretch to prepare the images. So, okay. You need a 16-bit photo editor. 8-bit need not apply. I do just cropping and minor things like a bit of sharpening, not much more. I use Light Zone, which is an open source package. Raw Therapy is also open source. There's an Astro package for
They
Photoshop.
don't have, you can't buy right zone now.
I'm sorry, say again.
You'll never buy right zone for 5 or 6 years. And then
Light Zone, the commercial package died. There is now a freeware effort. The package was donated to the freeware effort.
Oh,
And so it still lives.
okay.
That's what I did use for most of my cropping. But I'm gradually moving over to raw therapy as I'm learning to use it. Let's see. Okay, there's an Astro package for Photoshop, but I've seen reports that raw therapy is better. So if you have Photoshop, I'll find consider the package. But I wouldn't go out and get Photoshop without trying raw therapy first. The Image Magic package does a variety of things: resampling, format conversion, display. That's one of those big things that I spawn off as a sub-process and use a pipe. So it does all my multi-format input-output for me, so I don't have to figure out how to do that. I wrote my own histogram. That's a C program, but that again forks off. Was a GNU plot to actually do the plots. Let's see, image display, well, there's display, which is part of Image Magic, or XD, which is a shareware with source for personal use program. I think that's the
XD is still around?
Yep. Many of those images that you saw there, in fact, let's see, yes, those images that you saw there were being displayed with them. It's still there. It still works. And PixInsight is the premier astro imaging processing package. It costs about $270, $275. It's some number in euros. That's the approximate dollar number. It's reported to have a steep learning curve, but it's evidently head and shoulders above everything else. So I plan to, in fact, the month that I spent writing this talk would have likely been devoted to learning PixInsight. So it's on the horizon. And a few miscellaneous items. Sturdy mount is absolutely vital to get a good one. Stay below half its load capacity. Mine has a capacity of 44 pounds, and I have about 23 pounds, I think, loaded on it. And a good mount is maybe more important than your optics and your camera. The red dot finder is very helpful. You cannot aim a camera very well. You know, with a telephoto lens on, you can't aim very well. This is a hot shoe mounted red dot finder. I just put it in and I can get the camera within half degree. It's very good. The shoot with a north-up camera orientation. For one thing, it's the convention for sharing images. Almost all of my images there were north-up. I think only one of them was inverted for some other reason. It makes it much easier to compare with planetarium images or other people's images. Also, Stellarium has a north-up mode, so if you took a shot, you don't know where it is, and you're trying to compare the image on your screen with Stellarium to figure out where you are to get to where you want to be. That's called plate solving, by the way. This is eyeball plate solving. Having them oriented the same way is a tremendous help. Also, it's easy to combine data from multiple imaging sessions. So if you use different orientations on different nights, then when you register them, you'll lose a lot of your image size. If you use the same orientations every night, then it'll go better. And you learn to shoot with the camera upside down, in any orientation, in the dark, high field. I haven't had to learn yet with the operator in any orientation, but it's close. Also, you want to ultimately power everything from 110 AC or 12 volt DC. The 12 volt is so you can use it in the field with a storage battery. All Astro gear takes 12 volts, but otherwise you end up having to change your battery every hour to 2 hours, and particularly if it's out in the cold. You don't want to re-aim mess up your aim when you change the battery and so forth. And it's just so much better, out of sight, out of mind when you get that AC power in there. To get natural colors, again, use daylight white balance. A false color is often done in scientific images where they may be taking wavelengths that are not visible to the eye, and you have to map into something visible to display them. Or you can just take a visible light image and you can mix the colors around to suit yourself if it shows something or you think you're being collected. So you can do false color with any input. But as I've said several times, I want to get natural, or my goal is natural colors, so that's what I'm shooting for. Some cameras also have been modified to remove the infrared filter, so they have extended infrared sensitivity, since hydrogen emits strongly in near infrared. However, and your images will look a lot redder, but such cameras are not good for terrestrial shooting. Things will tend to look too red. And you can, one trick that you can use before you get to motor mount is that you can take fixed mount shots and stack them. Take them short enough so they don't streak. And then you can stack them. It's not nearly as good as much longer images because your read noise will be a major factor. But you can do a little better than you can without it. And computer control is a major win. Instead of being an operator, you become an executive.
We do need to start winding this down.
Okay, this is very close to the end. Instead of being an operator, you become an executive. You monitor and plan the next target, look at the stars, go inside, watch the meteors. Remote control is usually by a USB cable. Many Astro cameras use CCDs, but CMOS is getting better and better, and DSLRs do very well. There's a Dragonfly telescope, which is up to 48 Canon 400mm f2.8 lenses, all run on a single mount, and that can cost far less than the big professional ones. For $2 million, you can make a 48 array instead of $1 billion for the big ones, and can see things that the big ones cannot see because of the dynamic range of those lenses. And one can do well with on a fixed tripod. One can do a lot more with a tracking mount, and one can image surprisingly dark things, even from lovely light-polluted Bedford. And then this is a pile of references, and I think for the references, it's probably best to send them to.
We'll put them on the website.
Yes, or they can go on the website. And we've run the full circle. So. So we're at 9 plus a couple minutes. Is there time for one or two quick questions? Okay, well, either.
How long is this for you? I mean, what is your evolution here?
It took me about 2 years to, once I started doing the heavier duty stuff, about 2 years. And I didn't have a mentor, so I'm basically learning it on my own. Some things would have been much easier for a mentor to say, use this package. Instead of having.
So is a lot of this also from the community of people who are doing this sort of thing?
Well, I certainly had access to them through the internet. So I had help from Sean. Sean's a traditional eyepiece astronomer. His background is that. So I had help on things like the mount here and that sort of stuff. But things like the photography is something that I basically had to learn on my own. And there's another organization, Amateur Telescope Makers of Boston, where there are knowledgeable people. And, well, we have at least several members of it here. And I'm also a member. I know some of the astrophotographers there and get to talk to them. But it's the learning curve is both deep and broad. Yep. And I'm just an intermediate at this point. So I still have a lot more to learn. And for things like the math part, I guess I forgot to mention it. There are a lot of simple things added together. In fact, this whole thing is a lot of simple things added together, so that if you take it in pieces and then put them together, it's much easier to understand.
Right.
And when you're out in the dark, working with it in the cold, I've been out to 4 degrees all night, then when something goes wrong, it makes debugging extra interesting and the like. Just part of the fun. Or in other weather, you sit there slapping mosquitoes, hoping that they're not carrying AAA you're shooting. So, yeah.
Right.
So I guess that's it then. Thank you.
Yeah, thank you.